Hey guys, Mr. Backerberg here. In this video, we're going to look at numerical derivatives on a calculator. So if we're talking about very small values of h, then the difference quotient, or f of a plus h minus f of a all over h, can be a good numerical approximation for what the derivative is. But there's also this thing called the symmetric difference quotient. And the way that goes is it's f of a plus h minus f of a minus h all over 2h. So what's happening here is we're actually looking at an h value on the right side of our point and on the left side, and we're kind of finding the average of that slope between those 2 points. So visually what's happening here, say we've got this blue curve. This pink line in here is the true tangent line at that x value of a. This first black line going directly through that point, that's the difference quotient, so the f of a plus h minus f of a all over h. But then there's this other symmetric difference quotient where we go that h distance to the left and this h distance to the right. And if we notice in here, if we're comparing the slopes of these two black lines to the slope of that pink line, actually this symmetric difference quotient's slope is a closer approximation to the slope of the tangent line. So this approximation is close enough for us to use for the derivative at a point in most cases, but definitely not all cases. So as far as the numerical derivative of f at a point a, or we can call this n-der of f of x at a, it's the number f of a plus 0.001 minus f of a minus 0.001 all over 0.002. And this is actually fairly easy for your calculator to compute, and your calculator is going to have an option in there to compute these numerical derivatives. So in this first example, we're going to look at computing a numerical derivative. So we're going to let our f of x function be x cubed, and we're going to do the numerical derivative to help us approximate the derivative at an x value of 2. Now before we get to using our calculator, I do want to show you that computing this numerical derivative is fairly easy to do by hand. So that numerical derivative, f of a plus 0.001 minus f of a minus 0.001 all over 0.002. If we're doing this x cubed function and we're looking at an a value of 2, then the first piece we would plug in that 2 for the a, so we'd be looking at f of 2 plus 0.001. Well, that's going to be 2.001 cubed minus, here if we subtract 0.001 from the 2, we get 1.999 cubed, and that's all over 0.002. And this is really easy for us to type into our calculator. If we do that, we should get 12.000001. But now let's look at how we do this on our calculator as well. Now, depending on if you have a newer calculator or an older calculator, your numerical derivative might look a little bit different, and I'll show you both ways. But in order to find that numerical derivative, we're going to hit our math button, and it should be option number 8 in your menu, this n-deriv. That's the numerical derivative. So if I choose that, if you have a newer calculator, it opens up this math print type option. And what we want to do first is we're deriving this at a specific x value, so I'm going to put x in there. Then inside of the parentheses, you want to type in the function that you're deriving. So we're doing x cubed. Now because I put an x variable in here, it automatically changed this variable to an x. And here's where we want to pick a specific x value that we're looking at. So we want to look at an x value of 2. So if I hit enter, it'll spit out the number 12.000001. So we can approximate the derivative of x cubed at 2 to be about 12. Now if you have an older model calculator, typing in your numerical derivative will look a little bit different. So I'm going to switch my mode here into classic mode. So now if I go math and then down to the numerical derivative number 8, it puts this n-deriv in there, but now it gives you an option to type some things in. And the very first thing that you want to type in is the function that you're deriving. So this is going to be our x cubed function. We're going to separate things in here using the comma. So we're going to differentiate at an x value of 2, and then I close up those parentheses. So we're finding the numerical derivative of x cubed at an x value of 2. I hit enter, and again it spits out that 12.000001. So we can approximate that numerical derivative at an x value of 2 to be about 12 for that x cubed function. Now, I mentioned before that the numerical derivative is a good approximation in most cases, but not all cases. Here we're going to look at doing the numerical derivative of the absolute value of x at an x value of 0. Now, based on what we already know about absolute value functions, because of that V-shaped corner happening at the x value of 0, absolute value functions are not differentiable at an x value of 0. There's no derivative at 0. But if we try to do it on our calculator, it's going to tell us something different. So I'm going to try to do that numerical derivative for that absolute value function at an x value of 0. And I said that we're going to run into some sort of issue here. So we're doing the absolute value function, we're deriving at an x value of 0, I hit enter, and it tells me that the numerical derivative there is 0. So this proves that the derivative cannot be defined as the limit of the symmetric difference quotient. This is showing that the symmetric difference quotient works on both sides of 0 for this absolute value function. But we know that the absolute value function is not differentiable at 0 because the graph has a corner. And your numerical derivative can't detect the corner that's happening in there. Now we can also do some graphing of a derivative using that numerical derivative. So we're going to use the function f of x equals the natural log of x, and then we're also going to use that n derivative, or that numerical derivative, to graph out its derivative. So in my y equals screen for the y1, I already have that natural log typed in there. For the y2, I'm going to put in that numerical derivative, but I have to be careful how I'm typing it in. So I'm still doing the natural log of x, but I'm not looking at a specific x value here. So I'm just going to put x in there. So then when it picks x values to plug into the function, it's going to change each time depending on what that x value is. So then if I hit graph, my blue line is that natural log graph, and this red line is the derivative of the natural log. That's going to be it for this video. Thanks for watching.